Great. Okay. Hello, everyone. I'm Garrett. And
I'm Edric. I'm in the Lux lab, and
I'm in Jean-Francois' lab. And we have been developing and deploying an on-site test strip for lead and tap water. So I want to start with a quick anecdote. A couple summers ago, my air conditioner malfunctioned, and this is water damage that you see in the picture. And my landlord wasn't doing anything about it, so I had to call a technician. And this is me spazzing out on my landlord and quoting the technician. He said, "That AC system is older than Jesus." And I thought that was so funny. Just this idea that something could be older than Jesus was ridiculous to me. But in this case, we are dealing with something truly older than Jesus. This is Vitruvius's treatise on architecture, and he says, "Water is much more wholesome from earthenware pipes than from lead pipes, for it seems to be made injurious by lead, because white lead paint is produced from it, and this is said to be harmful to the human body." So before Jesus was even born, we have this guy connecting the dots that lead paint seems to be harmful, and lead pipes are made from the same thing, so maybe it's not so good. Fast forward to the post-World War I era, and in the 20s and 30s, cities across the US start to prohibit lead in plumbing. Why this happened in the 20s and 30s specifically is sort of unclear, but the best answer I could come up with is that this was the first industrial war, and so you have people who have never worked in a factory going into factories and learning about materials and how they can be dangerous. And despite this, in cities like Chicago, lead persisted because we have the Lead Industries Association spreading propaganda like you see here. And so Chicago actually required that plumbing be lead up until about the 80s when it was banned nationwide. And so we're still dealing with the fallout. We have the Flint crisis in 2014. And if you ask ChatGPT to list 10 of the most well-known contamination disasters, Flint will be on there. And this was a major event. The primary concern here was lead contamination. Though the discoloration that sort of drove a bunch of the media frenzy was from iron, the major health concern was lead. Part of the reason people were outraged is at this point we already had laws in place. Lead is regulated under the lead and copper rule. This was promulgated by the EPA in 1991, and it set limits for how much lead can be in tap water. The 90th percentile concentration can't exceed 10 parts per billion. And later in 2024, they updated this so that first and fifth liter samples have to be collected. And this has to do with the layout of plumbing. Generally, you have a service line that's made of lead, and then premise plumbing, or plumbing in your household, that's either copper or plastic. And we have typical volumes listed there, but that can change. If you have a big house, you might have more premise plumbing. Or if your house is far from the street, you might have a service line that has more water in it. Some issues with the lead and copper rule. This comes from a study that was conducted by the US EPA in Benton Harbor, Michigan, across the pond. They collected sequential tap water samples in households, and these are some extreme cherry-picked examples. But you can see this is the first dotted line is the fifth liter. So if you were to collect first and fifth liter samples, as the lead and copper rule prescribes, you would completely miss the lead peak. And in some cases, it can be extreme, getting up to 30 ppb, 4 times as high as what it would be if you collected a fifth liter sample. Other issues with the lead and copper rule. So the drinking water treatment plants conduct the sampling themselves. And in 2016, the Chicago Tribune published this article, and they say that Chicago was sampling households of employees in the Department of Water Management. And I think that's just because that's what's easiest. If you need to collect samples, you're going to ask the people you know, but you can see how that might introduce a conflict of interest. Another issue here, when you have really large municipalities like Chicago, it can be hard to get an accurate picture of what the 90th percentile is. They only have to sample 100 households. So our idea is to develop these test strips similar to a COVID test, so people are already familiar with how to use them. And then these can be distributed broadly, and you can get a much more accurate picture of what 90th percentile is. And at the same time, we perform our own unbiased sampling and lead quantitation in the lab, and that gives us something to compare and see are the test strips accurately measuring lead. So what we found is that lead concentrations were much higher in Chicago. The 90th percentile in the 8th liter was 17 ppb compared to Evanston's 7.5 ppb. And we think this may be due to higher polyphosphate concentrations. Drinking water utilities, they add polyphosphate to sequester iron and manganese, which can cause an odor or discoloration. This is normal. Lots of drinking water utilities do this, but it is thought to increase dissolved lead concentration. Since then, they've switched. They've gotten rid of polyphosphate completely. But when we did our analysis, there was more polyphosphate in Chicago than there was in Evanston. And we think this might be why we saw higher lead concentrations. What this suggests, because this is a normal thing to see, polyphosphate in tap water, a lot of municipalities, the only way to comply with the lead and copper rule is to replace lead service lines. And if you attended last year's watering hole with Gina Ramirez, you saw Chicago has 400,000 lead service lines, and that could take decades to replace all of them. So in the meantime, we have our test strips, and they leverage a chemical reaction involving lead-sensing DNA. This is not my side of the project, so I'm sorry if you have questions or if I don't explain it well. But we designed them specifically so that there's a faint test line at low lead concentrations, and then once 5 parts per billion is exceeded, the test line is darker in color than the control line. So we've iterated and improved the design of the test strips. In the first round, the data was pretty much unusable, but the second round, we got decent data. We got an R-squared of 0.2. In round 3, we got a little bit better, R-squared of almost 0.5. But when we had a PhD student operate the test in the lab, we got much better results. So we think that this may be due to user error, why we're seeing such low R-squareds in the field. Some of the common issues we saw were incorrect number of drops added to the test tube. You're only supposed to add 1 drop. These are actual pictures from our instructions.
I'd like to point out that those are Vanessa's names in the photo. Thank you.
My theory is people think 1 drop, you just need to get it wet or something. So they just add as many drops. Another issue that we saw, people put the wrong end of the test strip in the tube. That's a pretty reasonable mistake. And then another common issue we saw was misinterpretation of test strip results. So with COVID tests, if you saw any redness in the test line, that meant it was a positive result. Whereas with ours, you have to compare the test to the control. And so that's where Edric's app comes into play.
Yeah, so before I talk about the app, this is the example kind of actual lines, right? So you could see 0, the bottom is much lighter. But then once you go into 1, 2, 3, 1, 2, 5, 10, and 15, it becomes really hard to tell, right, how much lead there is. And so I came in, really my main contribution is to build an app, okay? So the way we test and I guess like calibrate the app is, you have these $3,000 proper commercial readers that people use for LFA tests. And we were thinking, well, all it does really is take a picture in a more controlled environment, and then it, gives you a reading of the actual band intensities. So then we were like, okay, well, maybe we should just try to build an app and, not have to make users all pay $3,000 to get accurate results. So the app is very simple. It uses everyone's cameras, right? And we print out a sheet where you put your strip on, and it has these tags that will automatically snap once it detects, correctly. Some aspects of this were like designed to control lighting conditions a little bit, and so there was a lot of little messing around there. Once it takes a picture, then it sends out to a server where it uses an AI model to figure out where exactly the test strip is, and then there's another model that cuts out just the 2 bands. After that, Tyler wrote some code to basically quantify the 2 bands, and then we basically get a readout of is it over 5 ppb or under 5 ppb. So so the slide shows kind of like the full thing. The web app interface is what you would see if you use this app, and then the back end is kind of what it actually is doing. So it does this cropping, and then it figures out quantification, and everything's stored in a server somewhere. So the most exciting result was really this bottom plot here, where we see this amazing correlation against the $3,000 machine. And this is all using a phone, with variable lighting conditions. And so this was the contribution. And this was really exciting, at least on our lab side, because this is a very real world kind of issue that was resolved with, a simple app like this. So.
Can I ask you a clarifying question?
Yeah.
This on the web app, is that using one person's phone, or is that multiple people's telephone?
Multiple. This is like round 3 results. This is like real, yeah.
And Edric made this app in like a week, by the way. So.
Well, with AI's help. But
Yeah. That's it. Thank you.